The most important method of solving problems in chemistry involves dimensional analysis. Dimensional analysis is based on two of the simplest rules in algebra. First of all, any number divided by itself is always equal to 1. And second, anytime you multiply a number by 1, it's equal to itself. What dimensional analysis does is it uses conversion factors, which is a fraction where both the top and the bottom are the same in meaning, but they look a little bit different. So they form a ratio equal to 1. That way, when you multiply something by a conversion factor, you don't change the actual measurement, but you do change the way it appears or looks. When we're solving dimensional analysis problems, we break it down into steps, but always start by writing out what you're being given and what you're asked to find. Then, identify the relationship between the given and the find. Sometimes the conversion will take more than one single step, so you create a plan for solving it. You can write out that plan if you choose to, and you can also write out each relationship that's involved in that plan. Write the given as a fraction, and then add brackets for each conversion factor. Add each conversion factor so that whatever units you want to cancel out. Then simplify, cancel, solve, and check units. Keep in mind that conversion factors that are based on definitions do not change your number of significant figures. They're considered exact numbers with infinite sig figs. So therefore, whatever number of sig figs you have in the number you start with is the same as what you'll have in your answer. Now, the prefix chart I gave you will explain how any prefix relates to the base unit. For example, if we're comparing grams to kilograms, put a 1 in front of the prefix unit. So it's what one of those prefix units is equal to, and then use the multiplier from the chart in front of the base unit. For example, 1 in front of kilograms, and 1 kilogram is 1,000 grams, or 10 to the third grams. So this becomes the relationship that we base our conversion factors on. For example, kilograms converting to grams. This is going to be one step. It is one step if you have a prefix and a base unit. Now, when we set up our conversion, we'll begin by writing the given as a fraction, but we write it in scientific notation to make things a little bit easier. So this would be 6 times 6, 1, times 10 to the 1, 2, 3, minus 3 kilograms over 1. That makes it a fraction. And now I write kilograms on the bottom because that's what I'm getting rid of. Grams on top because that's what I'm going to. 1 kilogram is 10 to the third grams. Kilogram cancels, and I multiply. I have 6.61 times 10 to the, these are multiplied, so this is a minus 3 plus 3, so that's 10 to the 0 grams. Now 10 to the 0 doesn't change this number, so it's 6.61 grams. 10 to the 0 is the same as 1. So this is my answer. In the next sample problem, we again have a prefix and a base, so it's one step. So we'll do 6.50 times 10 to the minus 1 kilograms over 1. And I'm getting rid of kilograms, so that'll go on the bottom. And I'm going to grams, so that's up top. 1 kilogram is 10 to the third grams. Kilograms cancels. I have 6.50, and then I add the exponents, so this is minus 1 plus 3, that's 2. So this becomes 6.50 times 10 to the 2 grams. And we could leave this in scientific notation or express this as 650 point grams to keep all of this significant. Next one, again, prefix and base, so it's one step. So for this one, 6.25, I don't need the 0 because it's not significant, times 10 to the third centimeters over 1. I want to get rid of centimeters and go to meters, So centimeters on the bottom, meters up top. It's 1 centimeter is 10 to the minus 2 meters. Centimeters cancels, and when we add the exponents, I have 3 minus 2. That gives me 6.25 times 10 to the 1 meters, which could also be expressed as 62.5 meters. If we have two prefixes, then we have to take a little side trip and convert to the base first, because that chart only tells us how to relate things to the base. So centigrams will be converted to grams first, then to kilograms. The nice part about laying out a plan like this is every arrow in the plan represents a conversion factor, and it's going to take 2 conversion factors to get the job done. So we'll begin with 6.752 times 10 to the 7th centigrams over 1. 2 conversion factors. And in the first one, we're getting rid of centigrams and going to grams. Centigrams on the bottom, grams up top. So this is 1 centigram is 10 to the minus 2 grams. Centigrams cancels. In the next step, we're getting rid of grams and going to kilograms. 1 kilogram is 10 to the 3rd grams, and gram cancels. So of course we have 6.752 still. And for the times 10, we have this times this means 7 plus a minus 2, that's 5. And 5 minus 3 is 2. So that is our answer, which can be expressed also as 675.2 kilograms. So we got 2 more practice problems to try with this. First one, again, kilometers to meters to centimeters. So this will be 3.1 times 10 to the minus 2 kilometers. 2 conversion factors. First one gets rid of kilometers and goes to meters. And that's 1 kilometer is 10 to the 3rd meters. Kilometers cancel. And then in the last one, it's meters going away and taking us to centimeters. 1 centimeter is 10 to the minus 2 meters. Meters cancels. I have minus 2 plus 3, that's a positive 1. Positive 1 minus a minus 2 is positive 3. So this becomes 3.1 times 10 to the 3rd centimeters. And for the last one, centimeters converts to meters before going to micrometers. So it'll be, again, 2 steps, centimeter to meter to micrometer. So 7.61 times 10 to the minus 3 centimeters over 1. 1 centimeter is 10 to the minus 2 meters. Centimeters cancels. And meters on the bottom. Micrometers up top. 1 micrometer is 10 to the minus 6 meters. So I have minus 3 plus a minus 2, that's minus 5. Minus 5 minus a minus 6 is plus 1. So this is 7.61 times 10 to the 1 micrometers. It's the same as 76.1 micrometers. When we're working with volume, there's 2 different systems of measurements that we deal with. One is based on liters, the other is based on cubic meters. So that means we have to be able to convert within both of those measurement systems and between those different ways of expressing volume. So let's start with the more difficult one, which is converting between cubic meters and say cubic centimeters or cubic milliliters. Take a look at the most basic definition of volume, which is based on a rectangular box. And volume is expressed as length times width times height. Now imagine that rectangular box has 3 sides that all measure 1 meter. To get the volume of that box, we would take 1 meter times 1 meter times 1 meter, and we get 1 cubic meter. But I'm actually expressing it as 1 cubic meter cubed. Bear with me, you'll understand why. We have 1 times 1 times 1 is 1 cubed. Yes, I know that's 1, but we'll leave it this way for a reason. And meter times meter times meter is meter cubed. For the same box, if we were to look at it in centimeters, 1 meter is actually 100 centimeters. But we agreed that those are equal. So it's still the same box, but this time the volume would be 100 centimeters times 100 centimeters times 100 centimeters, which would give us 100 cubed, and centimeter times centimeter times centimeter is centimeter cubed, which you could then mathematically express this as 1 million. But if we leave it alone, what we see is 1 cubic meter cubed and 100 cubed centimeters cubed represent the exact same volume. It's the exact same box. So what we could do is take out the cubes and express it as 1 meter cubed is equal to 100 centimeters, which is cubed. This is convenient because it helps us relate any measurements of volume that are based on cubic meters. We just got to remember that it's based on the relationship 1 meter is 100 centimeters, and then we cube all of the factors to convert. Now, let me show you how this goes into play. In this one, I have cubic meters and cubic centimeters. I'm going to use the metric prefix chart that I gave you in my conversion, but I am going to start out with switching this to scientific notation and getting 7.1 times 10 to the minus 5 cubic meters. Now, I want the cubic meters gone, and I want to go to cubic centimeters. So let's start with what is the relationship between centimeters and meters, and it's this. 1 centimeter is 10 to the minus 2 meters. Now the next thing I do is cube every factor. So this becomes 1 cubed, centimeters cubed, 10 to the minus 2 cubed, and meters cubed cancel. When you raise an exponent to a power, this 10 to the minus 2 is going to become minus 2 times 3, or 10 to the minus 6. So what I end up with is this number divided by the 10 to the minus 6. To get this, we subtract exponents, so it's 7.5 times 10, and it's minus 5 minus a minus 6. Minus 5 plus 6 is 10 to the 1, and the unit centimeters cubed, and we're done. And again, you can express this also as 75 cubic centimeters. This same process is used for cubic centimeters as well as for cubic millimeters or any other unit. Now, this problem, cubic centimeters to milliliters, is a little bit different. This shows us how to go between the two systems of measurement. This is based on a definition. 1 milliliter and 1 cubic centimeter are equal to each other. They're the same thing. So if I were to write this out in a conversion, here's what it would look like. 3.7 times 10 to the minus 3 cubic centimeters over 1. And if these are equal to one another, my conversion looks like this. 1 cubic centimeter is 1 milliliter. In other words, the unit changes, but the number stayed the same. So it's still 3.7 times 10 to the minus 3, but the unit is milliliters. Now, eventually we're going to be combining these two as a method to go between cubic meters, cubic centimeters, milliliters, liters, and any other relevant measurement, whether it's cubic millimeters, deciliters, whatever you might need. So we start with this basic plan for volume conversions. We can convert back and forth between cubic meters and cubic centimeters like we just did. We can convert between cubic centimeters and milliliters like we just did, and go between meters and liters. Not only that, we could even expand this further, changing cubic meters into cubic decimeters, We could change liters into centiliters, kiloliters, whatever we might need. So if we take a look at this problem here, we're going to need the entire plan. We're going to need to go from cubic meters to cubic centimeters to milliliters to liters. That means we're going to need 3 conversion factors to get this done. So let's start with 1.56 times 10 to the 1 cubic meters, sorry, a little bit sloppy, over 1. And in my first conversion factor, I'm going from cubic meters to cubic centimeters, but I do have 2 more conversion factors after that. Okay, so in the first one, meters to centimeters, it's 1 centimeter is 10 to the minus 2 meters. Cube all of this. And cubic meters cancels. In the next one, cubic centimeters and milliliters, they're the exact same thing, so it's 1 and 1. And that cancels cubic centimeters. And in the last one, I'm dealing with milliliters going to liters. 1 milliliter is 10 to the minus 3rd liters. Milliliters cancels. So doing math, this becomes 10 to the minus 6. And I have 10 to the 1 plus a minus 3, so that's 10 to the minus 2. 10 to the minus 2 minus a minus 6, which means positive 4, and this becomes 1.56 times 10 to the 4th liters. And again, with our exponents, that's 1 minus plus a minus 3, that takes it to negative 2, and negative 2 minus a minus 6 is positive 4. We have a couple other types of math to review. These are things that we use in Chem 1 and Chem 2, but in AP Chem, the calculations become a little bit more involved. For example, volume. Our basic definition of volume was for a rectangular box. That's length times width times height. Volume of a perfect cube is side cubed. Volume of a cylinder is going to be the area of a circle, pi r squared, times the length of the cylinder to get the volume. So volume of a cylinder, pi r squared times h. Volume of a sphere, 4/3 pi r cubed. There may be other specific volume equations that you need. You will have to do a little bit of research on your side on the side to get these. For example, suppose we need a shape that looks like a rectangular box, except if you look at it from the side, it's actually not rectangular, but trapezoidal, like this. That might require a little more involved math that you would have to do a little bit of research to get. Now, additionally, for volume, if we're using an irregular shaped object and calculating volume, the most important method you will use is the water displacement method. It's the best way to determine volume of an object as long as it fits into a large graduated cylinder to calculate the volume. The other calculation that we use quite frequently is density. Density is defined as the mass per unit of an area. In chemistry, density depends on what we are describing. Typically, grams per cubic centimeter is used to describe solids. Grams per milliliter is used to describe liquids, and grams per liter is used to describe gases. Now, comparing this to physics, in physics, density, which was represented by the Greek letter rho, was always calculated in kilograms per meter cubed. In chemistry, we do not use this for density. We use these because they help make the numbers manageable for each different type of object. Solids and liquids, the densities, yes, are numerically the same, but to describe a liquid, it's easier to measure it in milliliters than it is cubic centimeters and so forth. All right, there is one last type of conversion that can come into play in AP, and that is comparing the different temperature scales. Fahrenheit we seldom ever use. Typically we'll be using Celsius because we use Celsius thermometers in here. But these equations will show us how to change between Fahrenheit and degrees Celsius. And most of our work in here will involve these two equations. These allow us to switch between Kelvin and degrees Celsius. 1 degree Kelvin and 1 degree Celsius are exactly the same size and measurement. They just have, the two scales just have a different starting point. So to calculate the temperature in Kelvin, all we do is take the Celsius temperature and add 273.15 degrees to it. Whenever we need the Celsius temperature, we take the temperature in Kelvin and subtract 273.15. One thing to note with these is round at the end, and since we are just adding or subtracting, our final answer will have the same number of decimal places as what we started with here, and round that when you are finished. Okay, this pretty much covers everything in chapter 1 of AP. We will be doing calculations, problem solving, both drills and practice, as well as more AP formatted material in class.